Welcome to Flexcom software tutorials. These videos provide a practical overview of how to use the software and take you step by step through sample model creation and analysis. This worked example considers a freestanding hybrid riser arrangement. This is a complex model which includes a dual-bore vertical rigid steel riser tensioned via a buoyancy tank, with a connection to an FPSO through two flexible jumpers. Once the structural configuration has been obtained statically, a load case matrix of various vessel offsets and wave periods are considered. To create a new project, select New Project from the File menu. You will then be presented with options for defining a project name and a project folder. It is advised that you use a project folder other than the worked example complex folder in the Flexcom installation directory. This will ensure that you do not overwrite the original files and will allow you to use the original files as references to verify your own files should you experience any problems. Once the project is created, you need to add the first keyword file to the project. To add a keyword file, select New File from the File menu. Select a blank file template which uses the metric unit system. Then enter the name static.keyxm and create an empty keyword file. The file should open in the main document panel. You should also see the file added to the project in the file view on the left. We will begin model creation using the keyword editor. The majority of the central structure, including the upper and lower flex joints, the upper and lower frames, the outer pipe and the buoyancy tank, is modeled using a single line. A separate line is used to model the inner pipe. Another two lines are used to model the oil and gas jumpers. The first line is called central structure and is assigned a length of 650 meters. Its start and end locations are called seabed end, which is located at the origin, and buoyancy tank top, which has the coordinates x is equal to 650 meters, y is equal to 0 meters. The structural properties of the line vary along its length, so it is necessary to define a number of subsections along it. The subsections are called lower flex joint from 0 meters to 1 meter, lower frame from 1 meter to 10 meters, outer pipe from 10 meters to 615 meters, upper frame from 615 meters to 620 meters, and from 621 meters to 625 meters. Upper flex joint from 620 meters to 621 meters, and buoyancy tank from 625 meters to 650 meters. Suggested minimum and maximum lengths of 1 meter and 5 meters respectively are suggested for the outer pipe. It is desirable to model the upper and lower flex joints using a single element, so a suggested element length of 1 meter is specified, which is equal to the joint length. A constant element length of 1 meter is also suggested for the lower and upper frames. A constant element of 0.5 meters is suggested for the buoyancy tank. Beginner or inexperienced users may prefer to use the table editor. Data is entered in tabular format with the various rows and columns clearly labelled. A new table for defining element sets is now created in the table editor. This is added by right-clicking in the table editor and selecting Add Feature. The features are grouped together into logical categories and subcategories as appropriate. Flexcom uses the concept of element sets to define the physical properties of the finite element model. Groups of similar elements are logically combined into named element sets. Properties are then assigned on an element set-by-set basis. As upper frame 1 and upper frame 2 have identical structural properties, a single element set, called upper frame, is now created to group both of these sections together. In order to ensure that the automatic meshing algorithm positions a node on the upper frame at the correct elevation for the connection to the T-frame, a named location is defined on the central structure called central structure T-frame at a distance of 619 meters along the line. Note that you may move through the cells in the table editor using the tab or arrow keys. You can resize the table and keyword editors by clicking on the center bar, holding the mouse button, and then dragging the mouse vertically. This allows you to expand your preferred editor for increased usability. A second line, named inner pipe, is defined to model the inner pipe and is assigned a length of 605 meters. Its start and end locations are called riser lower end, located at x is equal to 10 meters and y is equal to 0 meters, and riser upper end, which is located at x is equal to 615 meters and y is equal to 0 meters. Minimum and maximum element lengths of 1 meter and 5 meters respectively are suggested for the inner pipe. The upper and lower ends of the outer and inner pipes are rigidly connected using bulkheads. The pipes are also connected at regular intervals of 25 meters using centralizers, and these are modeled using pipe-in-pipe connections of relatively large stiffness. Non-linear gap connections are modeled at all nodal locations, intermediate to the centralizers. Note that the keyword entries may be auto-completed by pressing the Tab key. Non-linear pipe-in-pipe connections may be defined using a power law approach, which is characterized by a maximum contact force and an exponential coefficient. The power law method is much more convenient than creating non-linear connections using explicitly defined pairs of force deflection values. Furthermore, power law curves automatically adhere to recommended guidelines regarding non-linear relationships, such as providing a smooth curve which is monotonically increasing and which avoids any abrupt changes in slope. Two separate lines, oil jumper and gas jumper, are used to model the jumpers, both having an assigned length of 350 meters. The start and end locations for the oil jumper are called oil jumper FPSO, which is located at x is equal to 695 meters, y is equal to 225 meters, z is equal to minus 1.5 meters, and oil jumper T-frame, which is located at x is equal to 619 meters, y is equal to 1.5 meters, z is equal to minus 1.5 meters. The start and end locations for the gas jumper are called gas jumper FPSO, which is located at x is equal to 695 meters, y is equal to 225 meters, z is equal to 1.5 meters, and gas jumper T-frame, which is located at x is equal to 619 meters, y is equal to 1.5 meters, z is equal to 1.5 meters. Suggested minimum and maximum element lengths of 1 meter and 5 meters respectively are suggested for both jumpers. The T-frame is modelled using two short lines. The first line, T-frame top, is 3 meters long, and its start and end locations are T-frame 1, which is located at x is equal to 619 meters, y is equal to 1.5 meters, and z is equal to minus 1.5 meters, and T-frame 2, which is located at x is equal to 619 meters, y is equal to 1.5 meters, z is equal to 1.5 meters. The second line, T-frame leg, is 1.5 meters long, and its start and end locations are T-frame 4, which is located at x is equal to 619 meters, y is equal to 0 meters, and z is equal to 0 meters, and T-frame 5, which is located at x is equal to 619 meters, y is equal to 1.5 meters, and z is equal to 0 meters. Each branch of the T-frame is modelled using a single element, so a suggested length of 1.5 meters is specified. In order to facilitate subsequent connections, a named location called T-frame 3 is positioned at 1.5 meters along the line T-frame top. The top and leg of the T-frame component were modelled using two separate lines, as illustrated previously in the star lines keyword. In reality, the top is rigidly connected to the leg, so a nodal equivalence must be established to join the two parts together. Appropriate node labels, T-frame 3 and T-frame 5, were automatically created as part of the line modelling, and these labels are now referenced. Similarly, the leg of the T-frame is rigidly connected to the central structure using another nodal equivalence. In Flexcom, a hinge is defined as an articulation element with zero rotational stiffness. A hinge simply constrains the displacement of its two connected nodes to be the same, while allowing free relative rotation of the adjacent elements on either side. Consequently, there is no moment transfer across a hinge element. Nodes and elements represent the most basic building blocks of a finite element model. Nodes represent the cornerstones of the finite element solution, while elements are used to define the finite element mesh connectivity. In some respects, the line modeling feature has rendered explicit element generation redundant to some degree, but the star element keyword is still retained in Flexcom for complete generality of model building. In this instance, two hinge joints must be created in order to connect the T-frame to the jumpers. The star element keyword is used to manually create the required elements, while the star hinge keyword is used subsequently to designate the elements as hinges. The model view provides a live structure preview facility available during model building. The window size can be resized by clicking and dragging the edge of the screen or using the Maximize button. Standard views are provided on the main toolbar. These include isometric view, plan view, elevation view, and right and left side views. As well as facilitating rotation, panning, and zooming, it provides other useful features such as displaying node and element numbers, seabed topography, water surface profile, and many more. Flexcom provides two different formats for specifying structural geometric properties. These are termed the flexible riser format and the rigid riser format. Properties are assigned to the model on an element set by set basis. The relevant element sets in this context are outer pipe, inner pipe, oil jumper, gas jumper, lower frame, upper frame, buoyancy tank, T-frame leg, and T-frame top. Sets are also created for the lower flex joint and upper flex joint, although the assignment of properties to these is slightly different to the other sets. Both the inner and outer pipes are made of steel, and their structural properties are specified in the rigid riser format. Properties are assigned under the following headings: Young's modulus, shear modulus, outer diameter, inner diameter, mass density, drag diameter, and buoyancy diameter. Flexcom provides a facility to apply coatings, and this feature is useful when modeling the effects of insulation or marine growth, for example. Each coating is characterized by its name, type, whether internal or external, thickness, and mass density. The outer pipe is coated with an insulation material. Structural properties for the remaining element sets are specified in the flexible riser format. For efficiency of presentation, these values have been prepared in advance and are now simply copied and pasted into Flexcom. You should pause the video now to allow you sufficient time to input all the required values. You can restart the video again when you're ready. In Flexcom, a flex joint is defined as an articulation element with a finite rotational stiffness. Note that the star lines keyword was used to create the flex joint elements, while the star flex joint keyword is used subsequently to designate the elements as flex joints and assign appropriate properties. In this example, the upper and lower flex joints are assigned a constant rotational stiffness of 20 kN per degree. For simplicity, the associated weight in air and weight in water inputs are all set to 0. The simplest hydrodynamic property specification in Flexcom is that of constant hydrodynamic coefficients that remain the same throughout an analysis. 5 coefficients are specified to model drag, added mass, and inertial loading. For simplicity, all elements in this example are assigned the same hydrodynamic coefficients. The star ocean keyword defines parameters relating to the external environment, including the analysis water depth, the density of seawater, and the gravitational constant. In this example, the hybrid riser system is situated in 700 meters water depth. Flexcom provides a comprehensive internal fluid modeling capability. In this example, both the inner pipe and the oil jumper are oil-filled, while the annulus between the inner and outer pipes and the gas jumper are gas-filled. The level above mudline input is used to determine whether elements are fully filled with fluid, partially filled, or empty, and also to compute the hydrostatic pressure. Note that the keyword entries may be auto-completed by pressing the Tab key. Two sets of inputs are required to completely define the response of a floating vessel to the ambient wave field. The first set defines the vessel's initial position. The vessel in this model is located at x is equal to 700 meters, y is equal to 220 meters, z is equal to 0 meters, and has an initial yaw orientation of 90 degrees with respect to the global y-axis. The second set of inputs relates to the vessel RAO data. As this data may be quite extensive, it is typically stored in a separate file, which is simply referenced by the main keyword file. The file with RAO data already exists in the Worked Example Complex folder and is named K2-HR-RAO.incx. This should be copied into the folder for this project. Flexcom offers a range of standard vessel profiles to provide enhanced visual appeal. You may choose to insert an FPSO, semi-sub, drillship, etc., or even define your own customized vessel. In this example, an FPSO profile is added with dimensions of 100 meters by 280 meters by 50 meters. Flexcom presents a comprehensive range of options to fully describe the constraints which are applied to the finite element model. The most widely used boundary conditions are constant, which are time invariant, and vessel, which are used to apply vessel motions. In this example, the base of the central structure is fixed in all degrees of freedom, and the upper ends of the jumper hoses are attached to the FPSO. Note that relevant node labels were created automatically by the lines facility during model building and may now be referenced when defining boundary conditions. In this example, the relevant node labels stemming from the line's keyword are called seabed end at the base of the hybrid tower, and oil jumper FPSO and gas jumper FPSO at the upper ends of the jumpers. Note also that when referencing node labels, you must enclose them in curly brackets. Separate data tables are used to specify constant and vessel boundary conditions, as shown on screen. Although not used in this example, it is also possible to define customized boundary conditions using a user subroutine facility, which provides for complete generality in terms of constraint application. An initial static analysis is typically run from 0 to 1 second using a single fixed time step, and this standard approach is adopted for this example. The type of analysis to be performed must be specified in each load case section. In this example, a static analysis is required. Database post-processing is the most powerful and widely used post-processing facility in Flexcom. For this example, full database storage is requested. A database post-processing section is added by right-clicking the top bar on the table editor and then selecting Add Section. The post-processing requests are specified before the analysis begins via the Standard Output option. The Standard Output option allows you to quickly request a summary of pertinent information. For every element set referenced, Flexcom produces outputs of effective tension, resultant bending moment, and von Mises stress for that set. In this example, separate outputs are requested for the outer pipe, inner pipe, oil jumper, and gas jumper, respectively. Once the specification of data is complete, you should save the keyword file and run the analysis. When a run is in progress, you can monitor its status via the Analysis Status area. The progress bar is naturally more beneficial for longer dynamic analysis. You can view the analysis results using the plotting facility. Plot files have the extension .mplt. Here are snapshot plots of effective tension, resultant bending moment, and von Mies stress. The Flexcom plotting facility provides several options for zooming in and out. The quickest is probably to simply use the mouse scroll wheel. Alternatively, you can hold the Control key while dragging the mouse, allowing you to select a particular zoom area. Plot tooltips are very useful. The feature is enabled via the Toggle Tooltips button. When the mouse cursor is hovered over the plot, the tooltip displays additional information about the data point, such as its location within the finite element model. The keyword parameterization facility means that a single keyword file is all that is required to model each load case, so you include all the required data in a single base keyword file, restarting from the initial static analysis keyword file. Create a new blank keyword file named offset.keyxm. You may define constant parameters within a keyword file and reference these parameters when defining input variables. If you choose to define any such parameter, their definitions must appear at the beginning of the keyword file, under the preprocessor section. For the purpose of this example, two new parameters called offset and offset folder are defined and assigned nominal values of -50 and near respectively. For the purpose of this example, we will examine two vessel offset cases, near and far, at plus and minus 50 meters, though, in practice, several more might also be examined. The star variations keyword is used to vary the values stored in the offset and offset folder parameters, which were created earlier using the star parameters keyword. The combinations keyword is used to control the names and locations of the generated keyword files, along with required analysis combinations. In this case, both of the generated files are called offset.keyxm, and their locations are based on the offset folder parameter, whether near or far. If you need to take a break at any stage, simply pause the video and restart it at your convenience. The star offset keyword is used to apply vessel offsets. The keyword entries may be auto-completed by pressing the Tab key. Note that the offset parameter is referenced in the keyword, rather than simply typing a single numerical value. The type of analysis to be performed must be specified in each load case section. In this example, a static analysis is required. Each offset analysis is assigned a unique name based on the offset direction, whether near or far. Note that any references to predefined parameters or any mathematical equations must be enclosed in square brackets as shown on screen. The restart facility allows us to specify that a particular analysis is to be restarted from a previous run to build up the full dynamic solution in stages. In a restart, the structural configuration at the end of the preceding analysis becomes the starting configuration for the restart. Here, the offset analysis restarts from the initial static analysis. For the offset analysis, the start and end times are set equal to 1 second and 2 seconds respectively, consistent with the end time of 1 second, chosen for the initial static analysis. A fixed time step of 0.1 second is used to apply the offset over 10 solution increments. Once the specification of the data is complete, you should save the keyword file and run it. Once you run the master keyword file, Flexcom automatically creates a separate keyword file in the near and far folders, corresponding to each vessel offset. These files should now be run separately. For the purpose of this example, we will examine 3 regular wave load cases, corresponding to wave periods of 8 seconds, 9 seconds, and 10 seconds, respectively. Combined with the near and far vessel offset cases, this will result in 6 regular wave keyword files in total. Create a new blank keyword file that uses metric units named regularwave.keyxn. Four new parameters called offset folder, period, period string format, and period text are defined in the star parameters keyword, and each one is assigned a nominal value for initialization purposes. Period is the governing parameter in this example, which will be varied in order to stimulate different wave periods. The format function is used to provide neatly formatted period numbers with 2 digits. Note that any references to predefined parameters or any mathematical equations must be enclosed in square brackets as shown on screen. Character expressions may be created by combining text and numbers as illustrated by the period text parameter definition. In this example, there are 2 parameters changing, namely period and offset folder. Period variations include 8, 9, and 10 seconds, while offset folder varies between near and far, as before. The names of the generated files are based on the period parameter. The other parameters, period string format and period text, are used to create a neatly formatted period description. The combinations table is used to control the names and locations of generated keyword files, along with the required analysis combinations. In this example, the new files are placed in subdirectories based on the offset folder parameter, near and far. The file names are based on the period text parameter, resulting in file names such as Wave08S, Wave09S, and Wave10S. All combinations of vessel offset and wave period are considered, so a total of 6 files are generated. A load case section is added by right-clicking the top bar on the table editor and then selecting Add Section. The type of analysis to be performed must be specified in each load case section. In this example, a dynamic analysis is required. Each dynamic analysis uses an appropriate regular wave period based on the period parameter. A unit wave amplitude is used in all cases. Note that the period parameter is referenced in the keyword, rather than simply typing a single numerical value. Appropriate time variables are computed based on the regular wave period. Each dynamic analysis runs for 5 wave periods, with the loads ramped on over the first wave period. A fixed time step equal to 1/20th of the regular wave period is used. The regular wave analysis are restarted from the offset.keyxm file. Each wave analysis is assigned a unique name based on the offset folder parameter, whether near or far, and the period text parameter, which alternates between wave 8 seconds, wave 9 seconds, and wave 10 seconds. Database post-processing is the most powerful and widely used post-processing facility in Flexcom. For this example, full database storage is requested. Flexcom provides a powerful facility for generating a summary output file. The output is in a succinct format and could, for example, be pasted or inserted into a study report, or perhaps included as a report appendix. The standard output option allows you to quickly request a summary of pertinent information. For every element set referenced, Flexcom produces outputs of effective tension, resultant bending moment, and von Mises stress for that set. In this example, separate outputs are requested for the outer pipe, inner pipe, oil jumper, and gas jumper, respectively. Once the specification of the dynamic data is complete, you should save the keyword file and run the analysis. Once you run the master keyword file, Flexcom automatically creates separate keyword files for each individual wave analysis. These files should now be run separately, using the Run Folder option. Flexcom provides a range of options for performing a sequence of analysis without user intervention. These include folder running, branch running, and route running, and all of these options are available in the file view. When you initiate a job from the file view, the job is assigned an appropriate name by default, depending on how the job was initiated. In this case, the job name is consistent with the name of the containing folder. As you can see, this job is currently in progress, as indicated by the rotating circle icon to the left of the job name. The green tick beside the analysis title indicates that the analysis has completed successfully, without any warnings or errors. Keyword file interdependencies are readily evident at a glance in the file view. Specifically at the top level lies the initial static analysis, which represents the starting point for all subsequent restart analysis. At the next level come the near and far vessel offset analysis, which restart directly from the initial static configuration. Next are the dynamic regular wave analysis, which are linked to the relevant offset analysis. Unlike the database post-processing performed for the initial static analysis, no plot files have been requested or created in this instance. Instead, each regular wave analysis produces a tabular summary file. Here is some sample summary output, corresponding to the 8-second regular wave analysis for the near vessel offset case. You can examine the other tabular summary files created for the other load cases at your convenience. If you are performing a range of analysis, the Summary Post-Processing Correlation Facility provides a useful means of assembling all the pertinent summary output data across a range of load cases into a single document. Create a new blank keyword file named correlate.keyxm. For simplicity, all the available data from the regular wave analysis will be correlated. Note that the keyword entries may be auto-completed by pressing the Tab key. Once the specification of the summary correlation parameters is complete, you should save the keyword file and begin the post-processing run. The summary correlation process produces a tabular summary file and spreadsheet-based output. For every parameter which is correlated, a summary table is presented. The parameter names correspond to the descriptive titles assigned to the outputs during the creation of the summary output files. Summary outputs include analysis title, maximum value and corresponding time of occurrence, minimum value and corresponding time of occurrence, mean value, range, standard deviation, file name, and path of database file. After a dynamic simulation, the model view provides a playback option to examine the structural response. The video can be played at different speed settings, and it can also be stepped through frame by frame for a more detailed inspection. The model may be rotated by left-clicking on the screen, holding the mouse button, and then dragging the mouse. The area of interest should first be placed in the center of the screen using the arrow keys, or panning with the mouse. In order to ensure a smooth rotation, you should click near one of the screen edges and drag the mouse in a straight line towards the other side of the screen. For example, if you would like to rotate in a horizontal plane, place the cursor on the left-hand side about halfway up. Click and hold the left mouse button and then drag the mouse horizontally from left to right. You can pan the model using the arrow keys on your keyboard. You can also pan by right-clicking on the screen, holding the mouse button, and then dragging the mouse. During panning or zooming mouse operations, a red circle appears in the center of the screen. This is a useful reference point either for centering an object of interest or rotating the viewpoint around it. Flexcom uses color contouring to graphically display element forces, such as effective tension or bending moment, and this provides the engineer with an intuitive visual representation of the finite element results. The model view window can be split into as many as 4 panes, each with an independent view. Each view has an independent camera position and independent draw options. Flexcom allows for the post-processing of analysis results using 3 possible design codes, including DNV F101, DNV F201, and API 2 or D. In order to perform some code checking, you should first create a new keyword file using the metric unit system and name it codechecking.keyxm. A code checking section is added by right-clicking on the table editor and then selecting Add Section. The first step in performing code checking post-processing is to select a code by which the result should be post-processed. In this example, the code selected is DNV F201, which corresponds to dynamic riser analysis. DNV uses the notion of functional and environmental loads in the determination of von Mises stress VMS, working stress design WSD, and load and resistance factor design LRFD. Environmental loads are those loads due to environmental conditions, such as waves, current, and wind. A functional load is defined as a load caused by the existence of the structure and by operation and handling of the system. For further explanation of these loads, refer to DNV F201. In Flexcom, the environmental load is usually considered to be the dynamic analysis, and the functional load is typically a static analysis, either static or offset. Flexcom will assume the analysis preceding the environmental load case is the functional load unless otherwise specified. The star environmental keyword is used to define these environmental and functional loads, along with the API design factor, the correlation option, and the element set name. DNV and API both employ a number of material-specific empirical properties in the calculation of the material utilization. In this example, carbon steel is defined as the riser material. Governing properties include specified minimum yield strength, specified minimum tensile strength, Young's modulus, temperature derating factor for yield stress, and temperature derating factor for tensile stress. The star sections properties keyword is used to specify which material definition corresponds to which element set. If a diameter or thickness is not specified, it is assumed consistent with the structural properties defined in the initial static keyword file, under the star geometric sets keyword. Once the specification of the code checking data is complete, you should save the keyword file and run the analysis. When a run is in progress, you can monitor its status via the Analysis Status area. The progress bar is naturally more beneficial for longer dynamic analysis. Results from the code checking post-processing file are presented in a number of ways. For every section, a plot file is generated for von Mises stress, LRFD, and WSD. In Flexcom, it is possible to superimpose two or more plots to facilitate comparison. This is done by opening a single plot and then adding other plots to it, by selecting another plot in the File View area, and then dragging it onto the plotting area. Once the small plot image appears on screen, you can release the mouse button to superimpose the second plot on the first. Two text files are also generated automatically with the file extensions .sud and .suf respectively. The SUD file is the main output file, and it presents the maximum LRFD, WSD usage, and von Mises stress values calculated at each location, and the times at which each of these occur. The data in the SUF file is provided mostly for verification or debug purposes and consists of the actual tensions and moments used in calculating the maximum utilizations. This concludes the second tutorial video, which considers a freestanding hybrid riser arrangement. If you would like further information on Flexcom, please send an email to software@mcskenny.com or visit our website. Thank you for watching.